All right, so I think we should start. The next talk will be by Farrukh Mukhamedov from the United Arab Emirates, and he will talk to us about hypercyclic, supercyclic, non-Archimedean linear operators.
Thank you, Khader. So first of all, good morning to everyone, good afternoon. So, and then I would like to thank to the organizers for allowing me to give this talk. Basically, this during this not easy time to organize a conference. It's also not easy. It's highly appreciated by the from me, but all to organizers. Khader, also you are doing a lot of job in this to organizing this section also. So let me turn to my talk. The talk will be about this hypercyclic non-Archimedean linear operators. So this work is done jointly with my collaborator, it's Otabek Hakimov. He's from Tashkent, Uzbekistan. So basically, we wanted to consider some kind of non-Archimedean analogous of the linear dynamics of linear operators. So basically, if we consider linear dynamics, so if we consider linear operator acting on a Banach spaces or some kind of basically some kind of over the complex or real numbers. I'm talking about right now about the classical setting. So then it would be interesting to see what will happen with iterations of this linear operator. So this was what is called started to investigate deeply, starting with the work of Kitai. This is done in his PhD thesis, and it turns out this linear dynamics of this dynamics of linear operators has a lot of interesting and rather not expected kind of properties. So one of them is called hypercyclicity, supercyclicity of operators. For example, shift operators. They have a lot of very interesting properties. So I would just recommend the book for the about the two books about in this direction is written by Bayard Mataron, and then another one is from German mathematician Eckermann, I think. So it's nice books where you can find very interesting information about all this stuff. So now the question is what will happen? Most of these investigations are done when the linear operators acting on a Banach spaces over the either real or complex numbers. And it was essentially used sometimes complexity of the field and the real numbers. So and then it's natural to ask what will happen in the case of if we consider this kind of dynamical systems from when we consider the Banach space over the non-Archimedean fields. So basically, the question is the same kind of question what we posed for the linear operators, but what we are going to consider the same question for the Banach spaces over the field of non-Archimedean fields. So basically, our talk, we want to discuss linear operators defined on topological vector space over non-Archimedean fields. And then we will show that the hypercyclic operators does not exist over the finite dimensional space. And then so we consider several properties of these examples of hypercyclic and hypercyclic operators. So basically, this hypercyclicity is for the operator over the Banach spaces over infinite dimensional spaces. So on the other hand, our attention to start to look to this paper to work was started initially with the work of Kochubey, Anatoly Kochubey. He started to look to this kind of operators. Basically, he started in the paper of 13 in the journal of p-Adic analysis. So by looking to the shift, so what kind of operator? Let us look. Just this was our motivation, basically, from where we come to this problem. So let we consider ZP unit ball in the QP. By QP, we usually mean set of p-Adic numbers, and I consider set of continuous functions ZP with the values of CP right now. Suppose CP is a complex p-Adics with a subnorm, and then consider operator defined by this way, which is linear operator. So this operator can be interpreted as an annihilation operator from the p-Adic representation of canonical computation relation from the quantum mechanics. So if we define these Miller polynomials like this, then it turns out this operator acts on these Miller polynomials, which are the orthonormal basis for this space, like a shift, you see. So correspondingly, this means that this T can be considered as a shift operator on the set of C naught. C naught is a set of sequences going to the zero. So this, and then he also considered some kind of properties of this shift, some kind of density of orbit. So this was done in the paper of Kochubey. Now the question is, what will happen in a general setting? Because in general setting, there was no any kind of a theory about this non-Archimedean linear dynamics when we did this work. And then we a little bit want to develop this theory for the non-Archimedean setting. So first of all, let me define some preliminary information. Maybe everybody knows here. So by the K, I always mean a non-Archimedean field. So, and then here for this one, it's this property is called the strong triangle property is called non-Archimedeanity. Okay, so always in our paper in this work, we always assume this K is non-trivial. So this is essential. So here is a very standard notations. So by B, we denote this closed ball, and then here by AR minus, we denote the open ball with the radius of R and M and the center of A. So this is standard denotations. So by K module, we denote it's as usual multiplicative group. No, this one we call it just the values of the norm, and this is multiplicative group. So this is a well-known theory lemma. If K is non-Archimedean valued field, then the value group is a dense or discrete. So this is a well-known theorems. And then we pair is called K normed space. If it is a K vector space with a non-Archimedean, with this non-Archimedean norm. So of course, we always assume this K normed space should be in our work, should be Banach space with respect to this usual metric. So usual examples of these spaces are this L infinity, C naught, what we going to consider in this talk. So in our investigations, we will use most frequently this lemma, which is maybe evident, but the proof is not short. So let be normed space. Then for any pairs X and Y in E with this property, we can find such a sequence lambda such that with this we have this property. So this property we will use to get some results about the hypercyclicity of the linear dynamics. So this is just technical lemma. So now we want to recall some notions. So x, y, take a topological vector space over a non-Archimedean field, but this is a note. Take note, all these notions are standard in the linear space or in classical or non-Archimedean space. All of them are standard. So by orbit we consider this set iterations, and this operator T is called hypercyclic if there is some vector in X such that its T orbit is dense in X. The corresponding vector is called, in that case, T hypercyclic. Set of all hypercyclic operators we denote it like this. And this operator is called supercyclic if this set should be dense. This set should be dense. And an operator is called cyclic if a set which is a polynomials is dense. And a set of what is called cyclic vectors we denote like CCT. Because clearly you have this kind of inclusion. Of course, hypercyclicity implies supercyclicity, supercyclicity implies cyclicity. So we have to again stress here, hypercyclic operators on a Banach space should have this property, otherwise they become contractions. So now in this section I am going to talk about the standard properties of these hypercyclic and supercyclic linear operators. So we have the following proposition, which is also valid in the real setting. Here also we have in the p-Adic case also, if X is a non-empty set, finite dimensional vector space, Banach space, then T is not hypercyclic. So proof is very easily. It is almost standard with goes the same lines with classical ones. So here we also have a transitivity theorem, which is some kind of connection with topological transitivity and hypercyclicity. It turns out if X is separable F space, then two conditions are equivalent. So first is hypercyclic, and second one is topological transitive. So that means that for any two non-empty open set, one can find such an N. This intersection is non-empty. And this allows us to prove under the separability condition, if it is T hypercyclic, then this set must be dense in the G delta set. So these are another one is another important notion in this theory is called hypercyclicity criterion, which says the following one. So it is given in the paper in the PhD thesis of Kitai. So what does it mean? If we call it T satisfies hypercyclicity criterion, if we can find increasing sequence of integers nk in two dense sets d1, d2, and a sequence of maps such that we have these three properties should be satisfied. So basically the question is the following one. If this hypercyclicity is satisfied, do we have what is called do this our operator will be hypercyclic? So it turns out if satisfies hypercyclic criterion, then it is indeed hypercyclic. The question is another also question is if operator is hypercyclic, do we have a reverse implication? But this still at the moment not clear in a general setting. Therefore, this question is still open in a general setting. So, and then to get some kind of interesting result, we use this definition, which is about a quasi-factor. This is in some sense It is called reducing the mapping to the smaller part, and then make a topological conjugacy of this T naught and T. So then if you have this kind of, this is a technical lemma, I don't want to stop here. So here we have the following result. If T is a hypercyclic on a separable space, then for every x, we can find y and z hypercyclic vectors such that x can be written as a linear combinations of these two vectors. So this also theorem, all these theorems are, again, I have to stress here, all these theorems are well known in the real case, but we are here proving them to be consistent with the non-Archimedean setting. So similarly, we can prove T is hypercyclic if we have this kind of analog of topological transitivity for this one. And then here also we have a supercyclicity criterion, but here we have only two conditions instead of three in comparing to the hypercyclic criterion. Here the same kind of theorem. If T satisfies supercyclicity criterion, then it's supercyclic. Similarly, we have the following one. T is a cyclic if and only if lambda T is cyclic for every lambda, and T is supercyclic, again the same. But take note, this theorem is not valid for the hypercyclicity because we have counterexamples here. So this means that this only proposition is true for cyclic and supercyclic operator. And the question is the following one now. Can we have some kind of examples about supercyclic, hypercyclic, and cyclic operators, concrete examples. So therefore, we want to consider these kind of examples on the set of C naught. I have to stress here, basically in the classical setting, the people are considering LP spaces over the real and complex numbers. But due to the non-Archimedeanity, if we in the p-Adics setting or non-Archimedean setting, these LP spaces are the same with this C naught. Therefore, only analog of LP spaces in the non-Archimedean setting is C naught. Therefore, we are restrict ourselves to the set of C naught sequences going to 0. So first we denote two spaces, C naught with respect to indexed by integers, and then with natural numbers. So by C naught not consider only this kind of finite linear combination of the bases. Of course, this is that is dense in these spaces. Okay. So we always assume that my C naught is separable, which means that my field must be separable. This is in our investigation. This is a crucial condition. So I cannot consider instead of K CP. I cannot. So now take a sequence, bounded sequence on non-zero element of K, and by standard way I define linear operator on C naught by the following formula, which is called bilateral weighted backward shift. Of course, here I assume one of these coordinates must be one of them not equal to 1. Otherwise, it's called bilateral unweighted backward shift. So by B, we call it just usual backward shift. This is a standard denotation. So it turns out we can prove the following result related to this hypercyclicity and supercyclicity of these shifts. So what does it mean? These operators BA shift is a hypercyclic if and only if I have this kind of condition. And supercyclic, I have again this kind of condition. So I have to stress here this from this theorem, we can obtain the following immediate corollaries. So if it's supercyclic, this is a theorem what we already have. So if weight is symmetrical to the norm, then it's not supercyclic. This is one condition. And as one is a bilateral and usual shift, then it is not supercyclic. Moreover, this also will be not supercyclic. And another property is a very interesting property, which is really comes from the non-Archimedeanity property. If we have two weights with this property, then this is supercyclic if and only if this one operator corresponding to the dominated one is hypercyclic. So again, I have to stress here this theorem and these two corollaries will be the same, but the corollary this one is purely non-Archimedean, because this in the proof is essentially used is a strong triangle inequality, and then here is a corollary. The counterexample shows that. So here hypercyclic, but the way is not, it does not satisfy 4.1. Correspondingly, this theorem is not valid, or corollary 4.1 not valid in the case of real numbers or in the classical setting. So here we have this shows that essential differences between classical and non-Archimedean settings. So now we can formulate the following theorem also. If I have this set weight, and suppose all of them are not zero, then this shift is cyclic. So this means that in this C naught natural number, it's always cyclic. In particularly, this also will be cyclic. And then backward shift on naturals, it also is cyclic. And so here again the same definition. So now I'm considering the what is called space C naught n. But before we had we considered Z. So we have the same definition. Unilateral weighted backward shift. So here we have the following theorem: any unilateral backward shift on is supercyclic. It's always supercyclic. You see. Moreover, if it is hypercyclic, it is hypercyclic if you only have this property. So this is this difference between Cn and Cz. So moreover, we have the following condition: operator is supercyclic, and then is also supercyclic if and only if this lambda should be more than strictly 1. Here all the norms in the case of non-Archimedean field. Here is the hypercyclic. So now let us consider more complicated examples, which are in some sense perturbations of one and with a shift. So this kind of operator. Now we are interested in this perturbation of I with a lambda mu. So this is in some sense related to the resolvents of the operator of the shift. So it turns out this operator T lambda mu is not supercyclic for all lambda mu on CZ. See. And then as a corollary, we immediately get this operator is not even hypercyclic because supercyclicity is weaker condition than hypercyclicity. So therefore, we want to consider these operators on C naught because in the Z case, we couldn't get any kind of non-trivial examples. Therefore, let us stick ourselves to the C naught natural numbers. In this case, we have the following theorem, which is says the following: T satisfies hypercyclicity criterion. T is hypercyclic, and then we have this inequality. So explicitly for this kind of operator, these three conditions are equivalent. So to prove this theorem, we need to prove these several lemmas, which are collected in this slide here. So operator hypercyclic, if you have this one. So proof is a little bit long, but all lemmas also has also not easy proofs. But all of them is a proof of this theorem based on these results. So from this theorem, we immediately get the operator cannot be hypercyclic for any mu. But in the real case, it is hypercyclic when mu is not equal to 0. Again, this is you see some kind of differences between real and non-Archimedean cases. So what about the supercyclicity? In case of supercyclicity, we have this kind of conditions, which is equivalent to the supercyclicity and supercyclicity criterion. So then we have the following question: does there exist a hypercyclic linear operator on C which does not satisfy the hypercyclic condition? We are right now conjecturing that such linear operators on C does not exist. This is our conjecture. At the moment, we don't have any kind of answer in general setting, but this example shows that it's supposed to be. But in general, we don't know. So if someone who is interested, they can try to solve these problems. So now let us consider another kind of perturbation, but in this case, instead of usual shift, we are going to take weighted backward shift. Okay, in the previous theorem was B was taking a usual shift, but here we are taking weighted shift. So it turns out we already proved these theorems. We already know where these theorems. So based on this one, we can prove the following theorem. If I take a B bounded with B1 is 0, then TB this one is TB. This one is, we call it TB. Okay, this is denoted by TB. So this operator TB is supercyclic if and only if TB prime is hypercyclic when B prime is defined through the usual shift, backward shift. So this is some kind of connection between supercyclic and hypercyclic operators. So again, this theorem is a proof of this theorem based on the following lemmas, which are in some sense technical lemmas. First of all, we suppose to be cyclic operators, then this set cardinality must be at most 1. And another one is if supercyclic operator, then all B must be non-zero. And another one lemma is if it is hypercyclic, then all B must be non-zero starting from 1. Here is starting 2, here is starting 1, you see. Starting 2 is supercyclic, starting hypercyclic, starting 1, all coefficients of this shift must be not equal to 0. So this theorem lemmas allowed us to prove theorem 6.2. Okay. So now let us consider some examples for which all conditions of theorem satisfied. Okay, let us consider this operator. and then consider constant with the mu. Then this operator we have with this one. So we already know this is hypercyclic. If you know leave, mu is more than 1, so it is hypercyclic. So according to theorem, we conclude that TB must be supercyclic. So again, stress here, for a B with this more than 1, the lemma must show the difference between supercyclicity and cyclicity of the operators. So, but we want to give some kind of result about cyclicity. So in this case, we restrict ourselves to the p-Adic numbers. In this case, we have some particular result in this direction. If B is a weight with starting B2 is 0, and then the rest are not 0, then is a B double prime hypercyclic, then TB must be cyclic. Here, double prime is 2 times shift. This is some kind of again connection between hypercyclic and cyclic linear operators. So now we are going to give some sufficient conditions for the hypercyclicity of operators in the form of TB. So if B is satisfies this condition, so lim equals to infinity starting from 1, then T must be hypercyclic. So due to remark to what I already mentioned, if this is a starting 2 is infinity, then is operator supercyclicity. Because we already have supercyclicity is related with an index with 2. So now, after that one, we have the following corollary with the form of the operator. This is a supercyclic if I have this kind of condition. So what about necessary condition for the supercyclicity? So if my B is supercyclic, then I have this one. In the previous theorem was sufficient condition was here just lim, but the necessary condition here we are putting lim sup. And then at the moment we don't know, do this condition will be sufficient or not. We are right now we don't know this condition. So as I said, the condition is also about the same kind of question. Can this one replace with this condition also? So this means that at the moment all these necessary and sufficient conditions are we don't have any kind of what is called do these necessary conditions will be sufficient. This is right now open questions in general for this, even for this class of operators. So again, if operator is hypercyclic, I have the same kind of result. So this means that do we have this? Is it possible to prove this condition also will be sufficient condition? Again, what is called problem. So now, if we want to conclude, what we have already, we can formulate the following theorem. So when Bn is a constant, if B satisfies hypercyclic condition, this criterion mu is more than 1, this supercyclic, all of them are equivalent. It turns out for this spatial class, all these are equivalent. For this special class of operator, it turns out they are equivalent. And then we can, based on our previous results, we can formulate the following problems. Is it possible to find B such that TB is hypercyclic under this condition? or can we find such a supercyclic operator with this condition? Here I'm putting here lim_inf. Take note, lim_inf. And can we find such a B, which is hypercyclic, and but T square is not cyclic? So these are problems. Right now we are posing. Answer is right now is we don't know it. If you are interested, you are welcome to solve this. So here I can show some of the references. So this work, part of this work was published in the William Bulletin, and some part are right now not published. So please, if you have any questions, you are welcome.
Okay, thank you, Farrukh. Any questions? Ala, you have to unmute yourself. I see you're trying to speak.
Okay.
Yeah.
You can speak now.
A small question. Can one use a technique of hypercyclicity to prove the invariant theorem?
Sorry?
You have produced hypercyclicity. The p-Adics Banach theorem problem was solved by Sliwa. The subspace problem. That means that if I consider an operator, does there exist an operator without invariant success? You know this. Do you know the result of a Sliwa in p-Adics case?
Right now, I don't know, because this is the first steps at the moment we are trying to develop. Maybe this is a new stuff right now, because at the moment this stuff we are just started to this. Maybe this will open new direction also. At the moment, I don't know.
Okay.
Okay. Any other questions? Any comments? Okay. So we thank Farrukh again.
Thank you for your attention. If you have some kind of questions, you may directly email me. You are welcome. Thank you for your attention. Thank you, everyone.